Okay, this is our video lesson on Unit 7 and 8 Diagnostic. So here we go. The image of point A, -3, 4 under a dilation is 9, -12. What is the image of 1, 5 under the same dilation? So first things first, we have to look at the dilation that goes from A to A prime. A dilation is a multiplication operation. So I'm looking and saying, all right, -3 times -3 gives you 9. And I'm saying to myself, 4 times -3 gives me 12. So my dilation scale factor is -3. And I have to apply that to 1, 5. All right, so I'll do that. I'll take a dilation of -3 on 1, 5, multiply by -3, I get -3, comma, -15, which is choice 2. Okay, number 2, in which of the following transformations will the image of 3, 7 not become -3, -7? So these you can kind of take choice by choice. If I take 3, 7 and dilate it by a factor of -1, I'm multiplying by -1, I get -3, -7. So that would become -3, -7. A reflection in the origin. I can quickly do a diagram of this. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So 3, 7 is here. Through the origin, I'm going to go down. I'm going to go to the left 3 and down 7. So I'm going to do that again. The left 3 and down 7. And look where I end up. I end up at -3, -7. So that's not it either. A rotation of 90. So I start with 3, 7. Which I actually have drawn, but I'll draw it again. So I have my 3, 7. And you can do this on your paper. Okay, I can rotate this 90 degrees. It goes counterclockwise, boop, right there. And I hope that you see this point would be -7, comma, +3. So that is not -3, -7. By the way, the rule there, you can see it clearly for a rotation of 90. If you just do a couple of them or even just one, you can see the rule is -yx. My x and y switched and this guy became a negative. So that's the rule for that. And a rotation of 180. So if I just kept rotating this, so this was the rotation of 90. If I just keep rotating this figure, if I rotate it again, boop, I'm at -3, -7 yet again. So choice 3 is definitely the answer. Okay, number 3, a translation maps 2, -3 onto 5, -7. Which point has an image of 8, 6 under the same translation? The reading was critical. This was actually a test question from this year, and the reading got a lot of you. So firstly, I have a translation. I'm going from 2, -3 to 5, -7. And I got to figure out what that translation is. Translations are adding and subtracting. So I'm going to go from 2 to 5. Well, guess what? I just added 3. And then -3 to -7. Well, what happened there? I subtracted 4. So that's my translation. Now, this says which point has an image of 8, 6 under the same translation, meaning that there's a point that gets transformed by 3, -4 to give you 8, 6. This is the image. The image is the answer. The image is the output. When you look at the mirror, you are you, and you're looking at the image. You need to be there first, and then the image appears. So I have to figure out what that would be. So if I'm thinking, I got to take x and add 3 to it to get 8. Well, okay, hopefully you see, if I take x and add 3 to it to get 8, well, then x has to be 5. And if I take y and subtract 4 and to get 6, hopefully you see that y would have to be 10. And so this is 5, 10, choice 4. Again, I think the tricky part there is the reading, not the math. Okay, number 4 says, what is the image of the point P, x, y after a reflection across the line x equals 0? What is x equals 0? A lot of people struggle with this. X equals 0. Well, here's what I'm going to do. Here's x equals 1. This would be the line x equals 1. It's a vertical line. You can think, Mizal does this, excited lines. Jump up and down. I kind of like to think of it a little more mathematically. I think of, all right, well, this point is 1 comma 0. Say this point is 1 comma 5, 1 comma 7, 1 comma negative 2. And all those points on that line have an x coordinate of 1. So this would be the line x equals 1. Well, where would x equals 0 be? Because that's the line I want to graph. Well, x equals 0 is just going to be moved over here. Right? It's going to be a vertical line at 0. So x equals 0 is really just another name for the y-axis. So here's x equals 0. So x comma y, you know what I'm going to do? I'm going to pick a point for that. I'm going to pick 4 comma 1, just so I can experiment here. So 1, 2, 3, 4 comma 1. And I want to reflect this blue point over the y-axis, or the line x equals 0. Well, that's going to go to negative 4 comma 1. So what just happened? Well, 4, 1 became negative 4, 1. So x, y would become negative x, y, which is choice 1. Okay, onward we go. Number 5. Point A, 8, negative 4, is the image of A, negative 2, negative 4 after a reflection of which of the following lines? So I'm going to draw these out. So negative 2, negative 4 is the original point. Actually, let me draw this axis a little differently. So negative 2, negative 4 is here. And 8, negative 4 is the image. So that's way down the line here. So let me write this out. 1, 2, 3, 4, 5, 6, 7, 8. Negative 4, extend my axis. Here's my image. Okay, if I count from the 2 points, I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means my, say, locus point or midpoint would be 5 away. So 1, 2, 3, 4, 5 away. And therefore, my axis of rotation is, line of rotation is here, which I hope you can see clearly is x equals 3. It's a vertical line again, and it's cutting through the x-axis at 3. Okay? That last part alone. Okay. So number 4 says point H is located at negative 5, 7. What are the coordinates of that image after applying a rotation of 90? So again, you can physically do this. Let's say you just forgot all the rules. It's not a problem. You can physically do this on your paper. You can take your paper. You can plot negative 5, 7. You are all capable of doing this. Here's negative 5, 7. Okay, I'm going to take my paper. I'm going to rotate it 90 degrees, meaning one click counterclockwise. Click, just like that. And then I'm looking at my point. Well, my point is negative 7, negative 5. And it really is that easy. So if you forget the rules, you can do it that way. Now, just as a side note, and we saw this before in the video, we now know that the rotation gives us negative 7, negative 5. And I hope you can see what the rule is. Well, I have to switch the x and y. That becomes yx. And then this was positive 7. Now it's negative. I have to negate that. By the way, we're not negating this guy because the negative was staying negative. So we're not changing the sign there on the new y coordinate. Okay, number 7. Which composition is not an isometry? We talked about this word, isometry. Iso means same. Metry means measure. So we're talking about something that preserves size. Dilations do not preserve size generally, except if I'm dilating by a factor of negative 1 or positive 1, my size won't change. Okay? Because if I dilate by 1, I'm not really doing anything to the point. And if I dilate by negative 1, all I'm doing is reflecting the point through the origin, and I'm not changing anything. So right here I have, so 1 is out. 2 is a rotation followed by a translation. That will not do it. And 4 is a line reflection followed by a translation. That won't do it. If I dilate by a factor of a half, that's going to cut all my lengths down by a half. So choice 3 is not an isometry. Okay, number 8, which best describes the image of point xy after a translation of 4 units left and 2 units up? Well, 4 units left means I'm going backwards 4. 2 units up means I'm going up 2 units. Choice 4. Simple. Okay, point P is in quadrant 2, and the composition, rotation of 90 degrees, and a reflection of the line y equals x is applied to point P. Which of the following is a possibility for the coordinates of P prime? All right, and I'm looking at the coordinates, and I'm just saying to myself, okay, I have 1 in quadrant, so this would be in quadrant 4. This guy here is in quadrant 2. This guy here is in quadrant 3. And this guy here is in quadrant 1. So I'm kind of saying to myself, okay, I know I need to start with something in quadrant 2 because my point P is in quadrant 2. So I'm actually going to start with negative 3, 2. That's in quadrant 2, and that's one of the choices, and I want to see where I end up. Now, be very careful. When I do a composition of transformations, it's like a lunch line. So what's going to happen here is these guys, these transformations are hungry, and they're lined up to eat lunch. And the lunch is negative 3, 2. Well, guess who's closest to the lunch? The reflection in the line y equals x. So that's going to go first. Now, you may remember the rule. The rule for reflection in the line y equals x is literally yx. In other words, the coordinate switch. So I get 2, comma, negative 3. By the way, if you want to see that, if I have negative 3, 2, y equals x, so here's negative 3, 2. Y equals x is just the diagonal line where y is always equal to x. So it looks something like this. And I'm reflecting through that line, so I'm going to march down perpendicularly. Actually, let me redraw this. Sorry. I have to draw it very to scale to do this. So negative 3, 2. And you can use graph paper for this, obviously, if you have to do it on the test. So here, I just have to really draw this to scale. Okay, here's my line y equals x. And so I have to go perpendicular to this line. So I'm going to actually go down 1 over 1, down 1 over 1, down 1 over 1. So I end up meeting the line here. That's my perpendicular angle. And I hope that you see we end up at 2, negative 3. 2, negative 3. That's a reflection of the line y equals x. And then I'm going to rotate 90 degrees. We just did that rule, so I'm just going to apply the rule. It's negative yx, but I'm doing it to 2, negative 3. That's why there's a chain here going on. So I'm going to do that to 2, negative 3. I'm going to get negative yx, which gives me 3, comma 2. And that would end up being in quadrant 1, choice 4. Okay, that's definitely a trick on the trickier side. All right, number 10. Which of the following describes the transformation that maps A, B, C, D to A prime, B prime, C prime, D prime? I'm going to cheat a little bit. This is very easy on a smartboard to see, okay, here's how am I going to get this to here? And all I'm doing is I'm sliding it over. So that's called a translation. Okay, so now I know the rotations are out. And orientation is the order of the letters. Orientation is the order of the letters. And I hope that we see A, B, C, D goes clockwise, and it also goes clockwise in A, B, C, A prime, B prime, C prime, D prime. So they have the same orientation. Okay, number 11. Which of the following properties is not preserved by the transformation of maps A double prime, B double prime, C double prime, D double prime? Well, the area stays the same. As you can see, that A, B, C, D is the same size as A prime, B prime, C prime, D prime. So that stays the same. I want which is not preserved. The slope of CD. Slope of CD before, CD is a vertical line, my slope was undefined. C prime, D prime, it's also undefined, that got preserved. The measures of the interior angles of the quadrilateral. Again, we have to kind of figure out what we did here, but the angles did not change. My figure was not deformed. It was just sort of perhaps moved and flipped. Let's take a look at orientation. If I go from A to B to C to D here, I'm going clockwise. So my orientation changed. Okay, Number 12, the transformation which maps A prime, B prime, C prime, D prime, maps A, B, C, D, excuse me, to A prime, B prime, C prime, D prime is best described as, well, let's take a look. So I'm trying to go from the original to A prime, B prime, C prime, D prime. Well, if I look at this, it looks like, well, let's try to do this by process of elimination for a second. A line reflection. Well, if I flip this over any line, so here I can try flipping. I can flip left, right, and that would really go this way down. That's just going to reflect, that's my reflection, say, over the x-axis. Oh, sorry, I flipped it left, right. That would be a reflection over the y-axis. Well, that didn't happen. Okay, let's try this again. Let's flip it back to where it was, and we're going to flip it up, down. And then obviously you have to move it down here. That would be a reflection over the x-axis. So it's not just a reflection. Okay, a translation. Well, if I tried to translate this figure, if I slide it over, I hope you would see, I can't do that. I can't just slide it over. So that's out. A rotation. Okay, if I try to rotate this figure, so actually let me try to do that. Take this guy out for a second. Take a little snapshot of this. Okay, I'm going to try to rotate this figure. All right, that was not the way it was supposed to go. So we're going to try one more time. Ta-da! Okay, perfect. If I try to rotate this figure, I hope that you'll see, actually, okay, so I hope that you see, if we're going to rotate now, if I rotate, and I actually transpose one of these onto the other, when we rotate, move that back to the origin, we're not going to get the figure to be on top of the original. So a rotation is out. So now what is the actual figure? Well, let's see. If I were to translate this, sorry, excuse me, if I were to flip this over the x-axis, so I'm going to flip it up and down, okay? And if I were to then move that over, so I flipped here, I flipped over the x-axis, and then I moved over, then I get my figure. That's called a glide reflection. It's literally a flip and then a glide, or a glide and then a flip. So choice 4 is the answer there. Okay, number 13, easy question. You just have to remember how to really do it. We have triangle big has those vertices. I want to graph triangle B double prime, I double prime, G double prime, the image of triangle big under the composition of transformations. So B is negative 3, 4. Again, composition, the biggest thing to remember, you have to go backwards. It's read like Hebrew if you want to remember it that way. It's like a lunch line if you want to remember it that way. That's just how the notation is written. So we're translating 4, negative 5, and we're getting B prime. So that would become positive 1 and negative 1. We're just adding the x's and the y's. The x's to the x's and the y's to the y's. And then I reflect over the y-axis, which means I'm going to negate my x. So B double prime is I'm negating the x, so that's negative 1, negative 1. So I'm graphing that on here. In fact, I should probably graph the original on here as well. And there's the original. So I'm actually now going to graph B double prime, which is negative 1, comma, negative 1, and I will graph the others as well. Negative 1 is here, so that's B double prime. All right, awesome. So now I was negative 2, 1. My translation by 4, negative 5 was I prime, which is 2, comma, negative 4. And reflecting on the y-axis, I get negative 2, negative 4 for I double prime. And you have to label these. I double prime is 2, negative 4. That's here. I double prime. This is I double prime. Okay. And G double prime, G was 4, 2. So I'm translating 4, negative 5. So I'm getting 8, comma, negative 3. So reflecting on the y-axis, I get G double prime to be negative 8. Sorry, I'm kind of writing too much on. the board here. G double prime is -8, -3. That's my G double prime. And I'm going to graph that 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. And there's G double prime. So here's my new triangle. Notice they are the same size. All I did was translate and reflect. That doesn't change size. And in fact, that leads us to our next question. Is the transformation an isometry? Yes. The transformation does not change the size of the original triangle. Perfect. Is slope preserved? Slope is not preserved. I hope that's pretty easy to see. And you can be very quick with this. So for example, if I look at IG, the slope of IG is positive. The slope of I double prime, G double prime is negative. So this you can simply explain. For example, the slope of IG is positive, and the slope of I double prime, G double prime is negative. In fact, they are negatives of each other. They're opposites of each other. And then D says, what is the relationship between the areas of the two triangles? The areas of the two triangles are identical. So I can say the area of triangle big is not congruent, sorry, equal, and I'm writing in highlighter, whoops, is equal to the area of triangle B double prime, I double prime, G double prime, since the size of the triangle did not change. Okay, next up. All right, looks like we're on to circles at this point. So this is our Unit 8 stuff. And people forget the circles unit because it's one of those things that we do and we don't really see again. So circles are one of those things that you really have to kind of refresh your memory on. So in the circle, chords AB and CD intersect at E. AB is 14, so this whole segment is 14. EB is 4, and CE is 8. And I'd like to eventually find CD. The rule when you have two chords that intersect, and this is again a rule you really just need to know, and we proved it in class, but you wouldn't want to be proving it on the final. Piece times piece equals piece times piece. It comes from the similarity of triangles when you cross multiply. But again, that's not what I could ask you to prove that, but that would be in a kind of a structured proof. This here, you really need to know the rule. So my AB is 14, my EB is 4, so that means that AE is 10. I need the pieces. And I can't solve for CD directly. Ultimately, I want CD. So I want to solve for ED. I want to put an X on that. So I want to look at my pieces, okay? So if I travel along the first segment, AB, I have 10 times 4. So I did 10 times 4, that's along the same segment, equals 8 times X along the same segment. So I get 40 equals 8X, divide by 8, X equals 5. So many of you, this is actually a test question, so many of you picked 5 as the answer. I don't want ED, I want CD. And that CD is 8 plus 5, which is 13, which equals CD. So again, you have to really understand what the variable is in this equation. CD is 13, choice D. All right, 15. In the diagram below, quadrilateral ABCD is inscribed in circle O, and you have angle A is 75, angle B is 85. We eventually want arc DAB. Well, there are a few ways to go about this. One way to go about this is to know that inscribed angles are half of the arcs that they intercept. So if I take a look at angle A, for example, okay, that angle is 75. The arc that it lasers out to, or it intercepts, is 75 times 2, which is 150. And Similarly, well, if I look at that, they're asking me to find arc DAB. So arc DAB goes from here to here. Well, that's the remainder of the circle. So arc DAB is going to be 360 minus 150, which is 210, which is choice D. You could have also used the 85, although it's a little tougher. Another way to do this question is to realize we actually proved this theorem, basically from the stuff that we did. If you're in a quadrilateral that's inscribed in a circle, the opposite angles are supplementary. So this angle is 180 minus 75, which is 105. And then I can double that angle to get this arc of 210. So there's several ways to do that problem. Okay, number 16. In circle O, secants ABP and secant DCP are drawn and meet at point P. If AB is 11, BP is 4, DP is 12, I want to find CP, which is X. Another rule that we need to know, if I have two secants intersecting, or a secant and a tangent, this is what I call the woo-woo rule, or some people call it the whoa-whoa rule. In other words, the whole segment times the outside of it equals the whole segment times the outside of the other one. So my whole segment here is 15. Important. The entire thing, that's important. My outside part is 4 equals the whole segment D to P was 12. The outside piece is X. So now I have 15 times 4 is 60. 60 equals 12X. Divide by 12. And X is 5. Again, not a hard question, but if you don't know the rule, you're kind of done on a question like this. And this is where you really, I don't want to say memorize, but you need to know the rules. You need to have enough facility with them and enough practice with them so that you actually know the rule. Okay? All right, a couple more here. 17. In the diagram, accompanying diagram, we have segments RST, ST, and TR are tangent to the circle. SB was 3, BT was 5, TR is 13. I want the measure of RS. Important theorem to know for this question. Again, this is something you need to know. If I have two tangent segments coming from the same point to the same circle, they are the same length. So I get that in 3 ways. It kind of reminds me of an ice cream cone. So I have these guys are equal, those guys are equal, and the blue guys are equal. So now I just have to apply some numbers here. So I know that TB is 5, so is TC. I know that SB is 3, so is SA. Now, I also know that R to T is 13, so that leaves 8 for the blue piece, and therefore 8 for AR. And so they want RS. Well, RS is 3 plus 8, which is 11. And that's it. Again, another thing you have to know those tangent segments are the same. Okay, number 18. In the diagram of circle O, we have arc CA to arc AD to arc DB to arc BC is 2 to 5 to 8 to 3. We ultimately want the measure of angle BEC. So my arcs, CA, I'm going to put a 2x, that's the ratio piece. AD, I'll put a 5x. BC, DB, is 8x. And BC is 3x. That's how we handle ratios. Now I need to find out what x is. Well, all 4 of those arcs comprise the circle. So I can add them all up and get 360 degrees. So 5 plus 2 is 7, plus 3 is 10, plus 8 is 18. So I get 18x is 360 divided by 18, and x is 20. Now that doesn't answer the question. I want to find BEC. BEC is a floating or inside angle. That means it and the vertical angle are the average of the 2 arcs that they face. My analogy is you're summertime, you're hot, you're in the pool, you're happy. You're going to add the 2 arcs because you're in a positive mood. So 3 times 20 is 60. 5 times 20 is 100. So I'm going to take 60 plus 100 and divide by 2. So I'm going to get 160 divided by 2. It's the worst 6 I've written in my life here. Hold on. 160 divided by 2, and that's 80. And that's choice D. Okay, number 19. In the diagram below, In the diagram below, trapezoid ABCD has the bases inscribed in circle O with a diameter CD. If measure of arc AB is 80, find the measure of angle ADC. All right, since we have a trapezoid, we know that those two line segments are parallel to each other. If those two line segments are parallel, what we know is there's a theorem that says between parallel lines, you will have parallel chords. So I know, parallel arcs, excuse me. And so therefore, AD and BC are equal. The other thing is that DC is a diameter. So that means from C back to D is 180 degrees. So if I can do 180 minus 80, I get 100. 100 divided by 2 is 50. So now each of these arcs are 50 degrees. And now I'd like to find angle ADC. ADC is an inscribed angle, meaning that its vertex is on the circle, and that is half the arc that it intercepts. So I have 80 plus 50 is 130, and I divide that by 2 to get 65, which is the measure of angle ADC. Again, lots of rules you need to know. You can't walk into the test being like, well, I just forgot this. Lots of rules you need to know. All right, number 20. In the diagram of circle O, measure of angle ABC is 24. What is the measure of angle AOC? Very easy question if you know the rules. ABC is an inscribed angle. Therefore, the arc that it intercepts is double it. So that's 48. Since we're of circle O, O is the center of the circle, and the central angle is the same as the arc intercepted. So measure of angle AOC is 48 degrees. Some of you are probably thinking that you probably could have just jumped to the conclusion Okay, so I hope that you're coming, you could also jump to the conclusion very quickly that 24 times 2 is 48 and done it that way. Okay, 21. In the circle O shown below, diameter DB is perpendicular to chord AC at E. So we have a diameter that's perpendicular to a chord. DB is 34. So DB is 34. And AC is 30. What is the length of BE? So DB is 34, okay? That means since O is the center, that OD is 17. And there's a theorem that says if I have a diameter that's perpendicular to a chord, it bisects the chord. So if AC is 30, each of these guys is 15. Okay. Now, this is tricky. The best way to do this problem is actually to create a right triangle. So I'm going to create a right triangle here. And notice this side is 15. Now, let me actually redraw this. Excuse me here. I'm not being very neat. So AE is 15. And I'm drawing this radius in. Okay. Sorry, my smartboard keeps freezing, but we'll deal with it. Okay, so I have 15 here, and we said the radius was 17. And that will actually allow us to get OE. This is a tricky question. So we have 15 squared plus x squared equals 17 squared. 15 squared is 225 plus x squared equals 17 squared, which is 289. So if I subtract 225 from both sides, I get x squared is 64. Square root of that, and x is 8. So, sorry, that looks like negative 8. I meant to write positive 8. So if x is 8, and again, I want BE, so O to B is also 17, and I know this part is 8. Therefore, BE is 9. So 17 minus 8 is 9, and that is BE. That's a very hard question, but not impossible. All right, 22. One of these grand poobah questions here. You got all sorts of angle rules. All right, so in the accompanying diagram, AOD is a diameter, CFB is parallel to DA, CD is tangent to the circle. We have chords intersecting at E, angle BAF is 20. My strategy for this is to ignore what I'm trying to find and just go find stuff. So for example, I have this angle, which is 20. It's an inscribed angle. Therefore, the arc it lasers out to is double that. I get 40. See, right off the bat, I got something very easy. Okay, now I'm also been given parallel lines here. So I have parallel lines, and I have parallel lines, so I have two congruent arcs, very similar to one of the last problems, and we have a diameter, so this is 180 degrees. So 180 minus 40 is 140. 140 divided by 2 is 70. So now each of those arcs is 70 degrees. All right, and we just found arc AB. That's 70. Try getting all the arcs first. Okay, angle BEF. Angle BEF is an inside angle. So I'm going to look and say, okay, I have this angle and its vertical guy. The first guy is looking at the 40-degree angle, or arc rather. The other angle is looking at the 180-degree arc. So this guy is 180 plus 40 divided by 2, which is 220 over 2, which is 110. That's my inside angle analogy during the summer. He's happy. We're in a positive mood. We're going to be adding the two arcs. And we proved that in class rigorously as well. Okay, arc CB. Let me get rid of this guy for a second here. Arc CB, angle CDB. Angle CDB is being formed by a tangent and a chord. And there's a rule for that as well. The angle formed by a tangent and a chord is half of the intersected arc. So I can do 70 plus 40 over 2, which is 110 over 2, which is 55. Okay, you have to get the entire arc. D goes out to B, so it encapsulates from D to B. All right, angle BCD. Let me clean that up a bit. Get some stuff out of here. Gets a little cluttered sometimes. Angle BCD. BCD is an outside angle. So it can be gotten by taking the major arc and subtracting the minor arc. So my major arc is 70 plus 180. So I have 70 plus 180, which is 250, minus the minor arc, which is just this guy. C is lasering to F and D, so it's 70 over 2. Again, we're subtracting because we're sad. We're outside of the pool during the summer. Mom kicked us out because we were bad. 250 minus 70 is 180. 180 divided by 2 is 90. Now, some of you, I think, could assume that that's a 90-degree angle, but you really shouldn't. You need to show work there. And last but not least, angle CFE. CFE is tricky. CFE does not have a particular rule. Let me just clean this up a bit. My arcs were 70, 40, and 70. Angle CFE does not have a particular rule. It's formed by a secant and a chord. But what I can do, and that has no particular rule, but what I can do is actually get the inscribed angle that's adjacent to it by taking 70 and dividing by 2 and getting 35. And so this guy would be 180 minus 35, which is 145. And that concludes our video. Thank you.